So I want to maximize ELBO, right? So I'm going to use this estimate. So this is the estimate that we had. Right now, we have all of these guys clear. So this p theta for us is a Gaussian, is a conditional Gaussian distribution, whose mean is learned from z. And this QW here is, again, a mixture of Gaussians, right? Sorry, a conditional Gaussian, I'm sorry. This is QW given x. Sorry for that, right? Everybody's clear? OK. Now, OK, let me just open up the first term. So I want to compute log of the likelihood, log of p. So there is one constant. I don't care about that, log of c. So that's a way. And then log of the exponential term inside the Gaussian term, right? OK, so if you do the computation, that log of c is going to be some constant c prime. That's not important. The other thing is minus this norm divided by 2, right? And now, the thing that you need to estimate is the expectation of this guy. How you can estimate the expectation of this guy? The expectation is taken over z. So you're going to sample lots of z, given the Q network that you have. And then you're going to average it over those samples, right? So you can compute this guy. If you want to compute this guy, you just do this empirical expectation, right? And anything else is not important, right? There are constant coefficients, not important, right? Now, one thing that you can see here, it's going to make it a bit more clear why we call it autoencoding. If I want to maximize the ELBO, right? Now, this means that I should maximize this term, right? Clear? OK. If I want to maximize this term, what should I do to this term? I should minimize it, right? Now look at this minimize. This term that I want to minimize. This is x, right? The image, the data that I have, right? What is this guy? The output of the generator, right? At the mean side, right? So I have the generator. I compute the mean value. And then I want this mean value to be same as my image, my data, right? So I got from latent. I want to get back to my data, right? This is exactly what you do in autoencoding, right? So actually, when we were doing autoencoding and we built all of the empirical risk based on the intuition, we said that we need to minimize a squared error, so we're going to put MSE there, right? We were actually doing Gaussian modeling without knowing it, right? Everybody's clear? So at the output of the decoder, this is the decoder, right? Before I do the sampling. This is the output of the decoder. And at the output of the decoder, when I pass my latent, I want to see my data back, right? This is exactly what you do in autoencoding. You first get your data, you encode it to the latent, and then when you take the latent through the decoder, you want to get back to your data, right? So this is autoencoding. OK. But right now, the first term is already computed. So this is something that I can compute based on the things that I have access to. So that is going to be no problem. Now let's look at the second term. Second term is the KL divergence between Q and unit variance, zero mean Gaussian distribution. What is Q itself? That is again a Gaussian, right? But its mean value and covariance are learned, right? This is the only difference. OK, so what I want to do, I want to just find out what is the KL divergence here. So KL divergence, I can write down the definition, right? Expectation with respect to the first distribution, log of first guy divided by the second guy, right? Everybody's clear? This is just a definition of the KL, right? Now, next thing I'm going to do, I'm going to just replace Q and N inside this expression. Q is one exponential term, right? Divided by some coefficient. N is the same thing, right? The only difference is that the mean and covariance are different. So I'm going to do that. This is a bit messy, but let's just take a few seconds to make sure everything is right. So Q is sum of all of those I values, all of those entries. Every single entry is squared. divided by the variance, and then it's divided by, the corresponding coefficient, the multiply of all of those variances, right? So that's fine. This is the first Gaussian distribution. This is, the reverse version of the other one, right? So this term is 2 to power, like every single body here, Z, has 0 mean, so there is no mean here anymore. The variance is 1, right? And this is showing up in denominator. In numerator, I replace the variance with 1, right? And this is going to be the coefficient, correct? Everybody's cool? Okay. Now, this square root of 2 pi to power m is going to cancel out with this term here, right? Because in denominator, I have the same thing as well, right? Now, let me then open up this logarithm. If I open up this logarithm, first of all, look at this term here. This term that I have in denominator, sigma squared, right? I have multiply of all of those sigma squared in denominator. Now I'm going to write it down in some specific form. You tell me if it is right or wrong. This term, is it right? So I have log of 1 over sigma squared, square root of sigma squared. I'm going to take minus 1/2 out of it. So that is going to be minus is because it is in denominator, 1/2 because I have a square root, right? And then it is the product here, it's going to be a summation, right? Everybody's cool? Everybody can see that? Questions? Now, next thing that I'm going after is the term, the green term in nominator. If I take the logarithm of this exponential, what's going to happen? The term inside exponential, right? So I have minus here, I have sigma here, I have half here, right? So I'm going to factor all of them out here, right? So the only thing that remains is this nominator divided by sigma squared, right? So I'm going to replace it here, right? So that nominator exactly comes here, sigma squared in denominator, minus half summation is coming out, right? Everybody's cool? Okay. Next thing, that last term. The denominator already canceled out with this guy, so I don't need this one. This guy is going up, and when it comes up, this negative is going to disappear, right? But rest of it is the same, right? So I have 1/2, I have summation, I keep 1/2 summation. Here I have negative. Instead of plus, I'm going to put a minus, right? So it's going to be minus zi squared, right? So I didn't do any magic. It's just opening up the logarithm term, right? Questions? No question? Okay. Now, I have this term. This is a summation. That expectation could go inside the summation, right? Now I'm going to take this expectation inside the summation, and I take every single expectation one by one, okay? Let's look at it together. So I'm going to keep this minus half sigma summation here. Now the expectation is going to operate on the green term here. What's going to be the expectation of that green term? It's still the green term because the expectation is going on z, right? And I don't have any z showing up here, right? So it's a constant with respect to z, so I'm going to keep it as before, right? What about this term? What is the expectation of this one with respect to z if I assume that z is distributed with q? What is q? This is normal with mean. Okay, I'm going to drop all of those I and W's with mean eta and variance sigma squared, right? Now, I want to compute the expectation with respect to q of this term. Z minus eta squared divided by sigma squared. Okay, can I get rid of this sigma squared? I can put it here, right? This is a constant, correct? Now, the expectation of z minus its exact mean value squared. What should it be? Z is distributed by Q, right? You have one Gaussian variable. You subtracted it from its mean value. You squared everything. And you're taking its expectation. What should it be? This is the definition of variance, right? What is the variance? Sigma squared, right? So this guy itself is sigma squared. Sigma squared divided by sigma squared is 1, right? So this is going to be 1. What's going to happen to this blue term? 1. This is going to be 1. Everybody seeing that? Right? So when I take the expectation of the denominator, this is variable minus its mean squared. This is the definition of variance. So this is going to be variance. Variance divided by variance is going to be 1, right? So the blue term is going to end up being 1, right? So we have a 1 here. And then the last thing left is the red term. The red term is the expectation of z squared. Again, say that I have z distributed by mean value eta and variance sigma squared. What is the expectation of z squared? What is the expectation of z minus eta squared? It's the variance, right? Now, this guy, if you open it up, you're going to have that this term equals to the expectation of z squared minus eta squared itself. You can do it, right? Because you're going to see that this is like z squared going to show up, then you're going to have multiple cross terms which are going to be 0, and then you're going to end up with the last term, okay? Now, this guy equals to sigma squared, right? So what is the expectation of z squared itself? Sigma squared plus eta squared. Everybody is following? Yep. I mean, you can do it like this. So you're going to write it down in this form. So it's going to be expectation of z minus eta times z minus eta, right? Every single of them is 0 mean, right? Yeah? Okay, then you multiply, then you're going to see that. Okay? Questions? No question. So, moral of the story. What is the expectation of z squared? It is going to be the variance plus mean squared, right? And the mean value is eta. The variance is sigma squared. So it's going to be eta squared plus sigma squared. Since I have a minus, I multiply it with minus. Yeah? So you can redo this if you didn't follow it exactly. I could just put the final expression, but I didn't want to do that. I just wanted to give you the idea how you can compute it, right? But I do understand if you you do not see it exactly right now. It's all okay. You just take the last term from me. And I mean, just trust me, it's correct. Okay, so this is going to be the KL divergence. Now, the key point here in the KL divergence is that when I compute KL divergence, do I need to know anything about z itself, the sample? No. I just need to know the output of the mean neural network, the output of the covariance neural network, right? Because it only depends on sigma and eta, right? And these are deterministic values computed with those two neural networks, right? So I only need that to compute the KL divergence. I really don't need to do any sampling anymore as I need in the other expression. So at the end of the day, you can just play around with these expressions. So you can define this dummy function, which is log of 1 over u plus u. If you define it in this form, then it's not hard to show that this KL divergence is going to be 1/2 of this A function operated on the output of the covariance network plus the norm of the output of the mean network plus a bunch of one constant. Okay? And the key point about this KL divergence is that it only depends on the output of the mean network and covariance network. Everybody's clear? Questions? No question? Okay. So if you got no question, then let's try putting back those expressions inside the maximum likelihood term to see how we can do to maximize the likelihood. So we wanted to maximize this term, right, over all parameters inside it, W and theta essentially. And right now we have the two terms, right? And instead of doing maximization, we usually do minimization. It means that we are going to work with minus ELBO. And if we want to just put the minus ELBO, you see here KL is having no negative sign here, right? So both terms here are positive, correct? And then inside ELBO term, if we get back, sorry, here, this is having a minus, right? So those terms are going to be already multiplied with a minus. This other term already has, the first term already has minus. When I multiply everything with minus, those minuses are going to disappear, right? And I'm going to get rid of this coefficient 1/2. I'm going to get rid of all the constant that I have. And then you can just do a simple math to finally conclude that this risk term that you need to minimize is going to be this first term, which we talked about. This is essentially what you have in autoencoder. You have your original data minus the output of the generator. You want them to be the same, plus one particular regularization term, and that regularization term is the KL divergence, or proportional to the KL divergence. Questions? No question? So this guy is easy to use, right? So you have one data set. You're going to get all of those sample X. You are going to compute this one. You can simply compute that. And you try to minimize it, right? Over both theta and W. This is the conventional risk minimization you do in deep learning, right? So all of those variational inference and ELBO are going to just end up with a conventional, minimization of the empirical risk. Okay. So moral of the story: if you want to just train your variational autoencoder using maximum likelihood estimation, so essentially you're going to do ELBO maximization, and both of them are going to end up with minimization of this empirical risk, and the risk term is exactly the one that I showed you up there. This is, again, as I told you, autoencoding argument, because you have your X, which is the data, Z, which is the latent. You want the output of the decoder to be exactly your data, and you have a bunch of regularization terms which are trying to push your encoder to mimic the posterior of your data, right? Sorry, posterior of your latent. Okay. Now, so one question. I think you had a tutorial today. Do you want me to finish this part, or do you want me, because for the next session we are a bit relaxed, because after this section I'm going to only talk about like well-known variational autoencoder architectures, which is not that complicated. So if you are tired, I can, okay. Okay. So let me just summarize everything here. So it would be great if you just be refreshed before the session on Thursday. I mean, luckily it's not a long time, right? It's just 2 days. But the point is that right now what we have Gaussian encoder, Gaussian decoder. We wrote down the ELBO. We found out the empirical risk term that we have here. Now the thing that I want to do next, I want to just simply train this network. And if I want to train this network, I need to be able to compute gradient, right? Now, if I want to compute the gradient, what are the parameters that I'm computing gradient with respect to? W and theta, right? Now, look at this term here, the risk term here. If I want to take the gradient with respect to theta, everything is easy, right? This is a neural network. I have the output. I want to take the gradient. I do backpropagation, right? But what if I want to take the gradient with respect to W? What's going to happen? Here, I can do it easily, right? This is backpropagation. This is one function of output of the neural network. I backpropagate, I compute the gradient. This one is again backpropagation. This is a function of the output of a neural network. I backpropagate, I compute the gradient. What about this guy if I want to take the derivative with respect to W? But how? I mean, Q is not showing up inside this term that I can do simple chain rule, right? If I want to do simple chain rule, then I need to take the derivative of Z with respect to W, right? Because Z is the random variable generated by a distribution depending on W. But how you can take the derivative of one random variable whose distribution depends on your parameter, not itself? Z is not a deterministic function of W that you can use the classic chain rule, right? Z is a random variable whose distribution depends on W, right? So you do know that if you take the derivative, this should not be 0, but the point is that you don't know what is exactly the expression for that derivative. This is what I told you there is a bit of trick here, right? So we can do it either by doing importance sampling or a parameterization trick, yeah? And this is the things, I mean, this is very short. We're going to discuss, and by discussing that, you have everything you need to know to train one variational autoencoder, okay?